Okay, so hello everyone. So we have been pursuing this project in which we have been calculating this butterfly velocity for various holographic QCD models using two methods so far. First, we amongst ourselves did it using the entanglement wedge method. Second was this OTOC method, which is out of time ordered correlator. And we had part one of this, in which I had discussed some basic notions of OTOC, scrambling time, um, uh, for the boundary, just like for pure boundary picture. And I also just very briefly just sketched the procedure of how we would go about computing this butterfly velocity for our holographic QCD model. Today's talk, I don't know how many parts this talk will go into, convert into. Maybe 2 parts, because there is a lot to speak on this.
Already the second part, I think.
Yeah, so we already have one part, and maybe it can go to part 3. I don't know. We will see how this goes. But I have a lot to say, and hopefully, this entire thing of OTOC in holography will be pretty dry and clear after these discussions. And also, since we'll be very much concerned with the critical extension of the metric in order to make this method work, we will need to understand Penrose Carter diagrams, and most of our research group members were interested to learn in detail about these Penrose Carter diagrams. So I'll take a very good detour into Penrose Carter diagrams, and we'll see how it goes. Okay, so for this part, or for the future part, I don't know. These are the 4 topics that I want to broadly cover. So, firstly, I'll start off with, we have been saying this, that when there is a chaos in a system, we say that OTOCs vanish, and the commutator that I wrote down in the previous part grows exponentially. I would make this very precise, a very, very clear physical picture why this is the case, because we have just been stating this so far. Now we'll understand this physical picture, and understanding this physical picture is very important when we switch to the holographic picture, because this precise understanding will exactly translate into the bulk picture as well. So this would be understanding how vanishing of OTOCs translate to chaos in the system. So that would be the first part of this talk. Second, before switching to the holographic picture, we'll take a detour and learn in detail about these famous Penrose Carter diagrams, and they are extremely fascinating. And I hope I can deliver the beauty of these diagrams, the beauty of geometry that so beautifully gets encapsulated in these diagrams. That's the second part. Third part, the holographic picture of what I will say purely from the boundary perspective in the first part. And once we have all our machinery ready in our first 3 parts, we will finally dive into the explicit procedure of computing VB, which is the butterfly velocity. I just sketched very briefly how we will go about this. So depending on whether you all prefer, what detail you want me to go into for this, we'll go accordingly. So that's the brief outline of what I'm going to talk about. So let's start with this first part. Okay, so first part, understanding precisely how vanishing of OTOCs corresponds to chaos in the system. Before that, there were slightly like few confusions in the last part, like what exactly does the scrambling time mean, and how does it depend on each point, and there were doubts along those lines. And also there was this interesting picture that we have kept coming across, that namely that of the butterfly cone. So I'll explain that as well, how exactly do we get a butterfly cone. So firstly, okay, so I had written down this commutator. This beta represents a thermal state. I shouldn't be using beta because, okay. Now my beta is the temperature and T is the time, and this commutator was defined as this expectation value of V of 0 omega at some time T, commutator expectation whole square. And we said that this commutator decomposes into two parts, which is first is the time ordered part, which is not interesting, so I'm not going to write that down. Second is the OTOC, which has all the non-trivial information about the information spreading in the system. I also commented that this commutator for a wide variety of models goes like this: exponential of lambda L T minus T star minus mod X by VB. So of course you all know lambda, this is the Loganov exponent, this is scrambling time, this is butterfly velocity. Interesting thing I found in the literature, that this type of relation holds true for large and gauge series or CFTs, like I mentioned, but it also holds true for the SYK model. Also, it holds true for the spin chain, a wide class of spin chains. The example that I took initially to give the physical picture, this kind of relation holds true for all these three. So, right. So, firstly, coming to this scrambling time, I'll clear this notion of scrambling time. Scrambling time is a local notion. So what do I mean by local notion? Local notion means saying what a scrambling time is for the system only makes sense when we are okay. Maybe I should have put in position as well here. Let's say
the V is the position and W is the momentum.
No, I mean like the operators that I'm using, I've just mentioned the time at which I'm inserting them. I can also insert at spatially separated points. So,
okay, you can have 0, something.
Yes, exactly. So I'll do the correction because it's very necessary.
Commutators, expectation of commutator square, not
sorry. Yeah, sorry.
Yeah.
Square will be inside. Yeah, square will be inside, and this is V of x comma 0, and this is 0 comma t. So what I'm doing is I'm applying this operator W at origin of my space-time and at time t, and this is my operator at time 0 at position x. Okay. So
W is at origin.
W is at origin, yes.
And V is some
spatially separated
from it by X.
Yeah. Also, like I said in the previous part, it's more convenient to use future notions like plus t, but I later realized if you want to understand the physics very well, I think it is better to say that okay, this operator w acts at some past time t, that's why minus t, and this operator acts in the future, and that time at which acts is t equal to 0. So this operator comes before this.
Okay.
This is a little bit more easier to understand physically.
Last lecture you told that V is perturbation and W is...
Yeah. I'll come on to that exact notion. Yeah, so this is a local notion. Local notion means when I'm computing this commutator both at the same location. So I mean, like if I'm trying to compute this omega, this W at the origin, I will also compute X at the origin. Right, and once I am fixed at the origin, in my form for this commutator expression, this X goes away. I just have effectively this definition left. And now from this definition it's very clear, scrambling time is going to be my time where my commutator becomes order 1.
Basically, they both kind of meet.
Sorry?
This like X has matched up to that. B has matched up to W, basically. Or something.
Now since they are both at exactly the same point, now they are not spatially separated.
Because they have come closer, very like they have become one.
But like they can be very small even at very small times.
Okay.
Like if you look, t is the variable time, t star is a constant, what we are calling as a scrambling time. Suppose I put this t equal to 0.
Oh, okay.
So at time equal to 0, this is an like a very exponentially suppressed value. So this is not an appreciable value. This commutator begins to gain appreciable value, or I could say order 1 once I reach around this scrambling time. Yeah.
Okay.
Just before or just after, around this scramble. This is the length scale around which my commutator grows.
You mean to say that scrambling time is the time at the moment and after which the overlapping starts, basically, or when the they start to overlap, and then you have
overlap in a like overlapping will come into picture when they are spatially separated. Here it's simply when my commutator gains appreciable value. Physically, what this means is after this t star, the special time t star, all the locally the information will become locally unretrievable.
okay.
So
Basically,
that's chaos. Chaos kicks in. Like as
then
soon
you
as
can't go back and
yeah.
Okay.
So that's the physical significance of this scrambling time.
Wait.
Yeah.
To know it's at the order 1,
Yeah.
this appreciable value,
Yeah.
first we need to know T star, right?
Whatever t star may be, I'm saying this is the variable time. When this variable time comes closer to this t star, because then it is 0, right? This exponent varies and it is definitely going to be order 1, whatever this value of t star is.
Then what is this T star?
T star physically, like mathematically, you can describe this as a time scale where your commutator gains appreciable value. Like you can imagine, like physically you could think of it as, suppose I again have this usual spin chain. I have some operator, let's say sigma z at initial time, and suppose even v I choose is at again sigma z, but at a later time when I've let it evolve. Okay, so like the measurement of sigma z the second time, how is that perturbation that I caused because of sigma z in the past, it will affect the measurement that I'm going to do with sigma z in the future. So how much that the past perturbation is affecting is like, this is what it is physically encapsulating. Like more and more time we wait, more and more this perturbation is going to affect the initial configuration. And after this t star, like the information at that position is not going to remain retrievable anymore. Like chaos kicks in, I think. Yeah, after that chaos kicks in. The system becomes non-integrable. Okay. So whenever we define this T star, so this is a local notion. Local notion when we are concerned like at the operators both at the same position. So the time that it takes for two operators at the same position to make this commutator appreciable or order 1, that's how I would define the scrambling time. Okay. So this was for x equal to 0, right? This is how physically we can think about the scrambling time. Now suppose, so here it was 0, or this while I was saying x equal to 0, both at the same position. Now suppose there's some these operators that I'm acting. Suppose this is my space time. I act with w at some past time minus t, and at time equal to t equal to 0, I act v here. And I act my w at origin at time minus t, so they are spatially separated. Now in this case what happens is, like if I write down my expression again for this commutator, so for this non-zero x, what happens is, now at the scrambling time we saw that when at the same position okay, let me put it this way. Okay, so suppose I start off with t equal to 0. Okay, so t equal to 0, I haven't yet reached this scrambling time. I have an exponentially suppressed value for this. Okay, so now what this means is the overlap between these two operators, like the amount that w is affecting v, how much this w is affecting v, is exponentially suppressed. So like at time equal to 0, they both are not affecting each other at all. As I put my w more and more earlier times, what will happen is this t, suppose once it reaches, suppose that I talk about the scenario when this t is still less than t star and greater than 0. Okay, so I put a minus t, so I mean this t is positive, so I mean I'm acting this w in the past. Okay, so when I have this t less than t star, so in this regime, this term is also giving me negative contribution, this term is also giving me negative contribution because I already have a mod here. So this term is still exponentially suppressed before this scrambling time. Means appreciable, like this perturbation w is not appreciably affecting this future operator that I'm going to act v. As soon as I cross the scrambling time, now this term gives me a positive contribution, and if like this x is a very neighboring value of 0, this difference is not that high, and I start getting some appreciable value in the near locality. Now I let my time proceed even more. Now this has an even greater contribution. So now even I can go at further and further x, and I will have an appreciable value for my CBT. Is that clear?
Yeah.
So what after this scrambling time, this perturbation is now affecting the local degrees of freedom.
Okay.
Right, appreciably again. Even at t equal to 0, there is some effect there, but that's exponentially suppressed.
Yeah.
Right? So as soon as we go more and more above this scrambling time, this perturbation operator affects this v, affects this local degrees of freedom more and more, and there will be a certain time when it will start affecting this particular x position at which we are operating v on. So like now coming to the butterfly cone. So if I want to draw a space-time diagram for this, okay. So maybe this is my space axis, and this is my this is the above is my time axis, and this is my space axis. So we start off with time equal to 0. There is no information spreading. We keep going, we keep ticking along our time, and we reach T star. And up to this time T star, there is still no appreciable overlap or like effect of this perturbation operator on V. As soon as we cross this T star, this information starts affecting the local degrees of freedom. So like now it begins to spatially travel, this perturbation. So now I will have something like this.
Before that, there was no spatial kind of thing, right? Before T star.
Appreciable, again, appreciable.
Okay, it's like
exponentially suppressed before
it
T
was
star.
very negligible.
Yeah. So as soon as I come to my T star, now this perturbation is beginning to affect the local degrees of freedom, and the rate at which this scrambling is happening is governed by this butterfly velocity VB.
Okay.
So of course this is bounded by this. Suppose this is a light cone here. This VB is bounded by this light cone. It cannot travel faster than the light.
Okay. This is the first bound that we have for the butterfly velocity, which is the bound V that it cannot cross the velocity of light.
Yeah.
It
Right.
will always be less than velocity of light.
Right. So I hope everyone understands why this cone, because we have this spatial on the x-axis. So now it's propagating in the space as well, not only in time.
So how quickly will perturb?
Exactly.
perturbation affecting?
Exactly. How quickly, the rate at which it affects its neighboring degrees of freedom is governed by this butterfly, or is precisely this butterfly velocity.
The rate. That's why the rate.
Yeah, the rate at which the scrambling is happening.
Okay.
So this is the precise notion. Okay. So I hope now T star is a local notion, right? At the same position. Right. Yeah, I've explained the butterfly velocity.
Now,
Yeah.
what you're going to explain next?
Size of the operator. I just very heuristically said that the size of the operator is the region in which this perturbation operator is going to have its appreciable effect. I will make that concrete here. So now, suppose we invoke this perturbation at a sufficient time which is greater than the scrambling time. Okay. Everything, this spreading, the spatially spreading of information happens after T star. Okay. So can I claim that the size of my operator is going to be given by this regime?
Less than maybe.
Do you all agree with this?
Obviously, because it's inside that.
So this is like the distance. Distance is simply the speed times, the time times the velocity something is traveling at. Why I am subtracting this? Because for the time T star there is no propagation at all. All that propagation of information happens is in this interval. In this interval, because after T star the extra bit that I have. Okay. So one key takeaway from this: whenever I want to affect, I want to see the effect of my perturbation operator on some spatially separated operator V, I definitely, the bare minimum time I have to kick in my perturbation is this scrambling time.
Okay.
Or of course, definitely less than that, depending on how spatially separated these two operators are. Okay, so this is the precise notion of the size of the operator, and like if you substitute this mod x into this expression of CBT, this simply becomes CBT becomes order 1.
Yeah.
This is a definition I gave last time, the region where this becomes. Now I made it more concrete, like where is it exactly coming from.
Yeah.
Okay, so that was a few conceptually important doubts that were supposed to be clear. Okay, so moving on, now we'll discuss this physical picture of why vanishing of OTOCs precisely corresponds to chaos in the system. So we'll consider two states, something that I was just beginning to do in the previous part. We'll make it very much concrete in this part. I'll make everything clear. What do I mean by what I'm writing? This is my state 1 and this is my state 2. Okay, so these are the two states. Now what do I exactly mean by these states? Like, to understand the physical picture of both these two states, like everyone would be familiar with the Heisenberg and Schrodinger picture. Like both of them are equivalent pictures of quantum mechanics. In the literature, like people haven't explicitly mentioned that they're switching between the two pictures, but I think it's an important distinction to do. So firstly, I think to understand what these two physical states mean, I think Schrodinger picture is more intuitive. So I'll stick to the Schrodinger picture. In Schrodinger picture, I hope everyone knows that the states evolve with time, operators remain fixed, and the Heisenberg picture is the opposite, that operators evolve and the states remain fixed. Okay, and both the pictures are exactly equivalent. I can keep switching between either of them whenever I want. Okay. Right. So let's start with the Schrodinger picture. Suppose this beta is a thermal state that I have, some thermal state, right? And at t equal to 0, I start with acting on this thermal state and operator V. And when I write V of 0, it means I'm switching on my operator at time equal to 0, and I'm acting it on this thermal state beta. So pictorially, like if you want to understand this, maybe I can here beta, I'm just going to denote it as a horizontal line just for pictorial purposes. Okay, so when I act V naught upon this thermal state beta, this becomes like, this picture becomes like some perturbation and then, right? And again, yeah, I think I should write the positions again. Positions matter a lot. So say some spatial position V, I act my operator on it. Now what I do, I backward evolve my state. So of course the unitary time evolution for backward evolution is I plus I ht, where h is the Hamiltonian of my system, and I get to the state e to the power I h v times the state beta. Okay, so when I am backward evolve the system, I take this t to be sufficient enough such that my system thermalizes. Right? Thermalizes means it again just comes back to this original horizontal line beta state that I have.
Just a question.
Yes.
These are all quantum states, right?
Yeah, these are.
So there's no thermal bath.
No, like quantum states can be thermal states as well.
So it's like they are inherently thermal states.
Yeah, of course. Even our setup is a thermal system.
Okay, so the eigenstates act as thermal states.
Yeah, you could say that.
That's the idea of
It's
it.
basically whatever state you're dealing with at temperature T. I'm not changing my temperature.
Okay.
All this beta represents is that I'm keeping my temperature fixed at T, whatever states are there.
Okay. And are we dealing with ensembles here?
Ensemble? No, I don't think so. No.
So we are just have one system.
Yeah. Just one state will also do.
Because I have this confusion regarding the concept of temperature, and temperature is an emergent concept that comes from the statistical picture, but you have just one system, then how do you have that temperature?
Right.
Like temperature is something which is like a statistical
collective phenomena. Yeah.
So just one quantum state, and you have
I think you could take it as an analogy. Suppose I have a box, I have an idle, let's say, Fermi gas inside it.
okay.
All the constituent Fermi gas particles are going to constitute for a temperature at which that box is going to remain fixed. But like whenever we deal with a Fermi gas, we say that the system goes through a series of states, right? That state is constitute of the like the overall state of the system is the result of the state of each particle, each quantum particle that attains inside the box.
Yeah.
So the psi this beta that I'm talking about is the box of the is the state of the entire like a box which is constituted out of these quantum particles. You could think analogously to that.
There's another way that we can define temperature on. Okay, there's another way that we can define temperature on. Classically, if we have a degree of freedom for a bunch of particles, we can calculate the we can calculate the entire energy, which correlate to temperature very easily, and we have this calculation in statistics that give like how the energy is separated in its degree of freedom. This is like basically we know like and how energy is related to temperature, like kVT.
From the kinetic theory, it's like the
the
motion of the
so this energy relating to kVT is a statistical
energy relating to
like temperature.
Okay.
kVT.
Cavity.
Yeah, Boltzmann constant times temperature.
Okay.
So this can be used for single particle if we want.
Because I'm asking this because there's a whole notion of eigenstate thermalization hypothesis. There they consider to like this eigenstates as thermal states. So from where this idea of temperature is coming into picture when we just have one state?
So practically, possibly because I mean like every system has energy, so like we can interchangeably use energy as temperature defined through energy, some kind of temperature is defined. So
Okay.
So that's how even for single particle temperature are defined, something like that. Even though the notion of temperature itself came from
It's a macroscopic.
Yeah.
Okay.
Yeah, that's one way, or like you could just take that the state is in itself is a collection of some microscopic states, like it is in the case of idle Bose or a Fermi gas. Both notions I think are right to think of. Okay, so I backward evolve my state and I give my state enough time so it thermalizes again. So I again represent this with a horizontal line. Now what I do is I act my operator W now. So W e to the power I h t v beta. Okay. Now in the Schrodinger picture, like when I act my operator at some past time t, I can very well, and again I'm acting this at the origin. I'm forgetting the positions, but even though I am acting, I'm backward evolving, this is minus t, and I'm saying okay, there should have been a time minus t here.
Yeah.
But this operator in the Schrodinger picture is not going to evolve even if I get to t equal to 0. So I can very well just say, okay, it is going to be the same operator that I have at t equal to 0, because in the Schrodinger picture it is not evolving. It is the states that are evolving, and I'm taking care of that using this unitary time evolution.
But in the other picture?
I'll come to that. Those both are equivalent pictures, right? But
in
physically,
in that picture it will evolve, right?
But then states will not evolve. These exponential pictures will go away.
The combined effectors, which is what matters.
combined effect. No. Well, like when we are in a picture, we have to stay purely in that picture.
Okay.
We cannot mingle two pictures.
No, I'm not saying that. I'm saying that E to power IHT is like evolve with how we evolve, and then we have V of V. So in one picture, one stays constant. In another picture, the other. So basically, we can do either that or this.
Yeah. But like I'm choosing this Schrodinger picture because I want to make physical sense of what exactly the state is telling me. Like when I want to look at it from a chaos perspective, Schrodinger picture is very helpful.
Why is it so?
I'll be coming to that.
Okay.
So act with this operator W. Let's say this perturbation is this. It's a weak perturbation. Okay, now comes the notion of chaos. If my system has a chaos, even a slight perturbation, what I did is I had some initial state, I backward evolved my system, and I said now I'm going to add a very weak perturbation to this system.
Okay.
If this is a non-chaotic system, when I again forward evolve my system, I'm going to get this or very nearly this, even if there are going to be some minute changes. But if this is a chaotic system, I'm not going to get anything close to this.
Because it doesn't have the information of its initial state.
Like a small perturbation just destroyed everything that could have been. Again, the sensitive dependence on initial conditions. So
That
maybe
has
you
destroyed
can take
basically,
this.
basically destroys memory. There's no memory of the initial from where it came from.
Yeah. Like it destroys the rematerializing of this operator V of
Okay.
X.
Yeah.
This is a very subtle point. I think every student.
Yeah. If anyone has any doubt regarding it.
Like I can give a good example,
Okay.
a very physical example. Suppose I have a bath. There's water in it. Okay. Suppose I engineer a very smartly. By the way, water baths are extremely chaotic systems. Like black holes are in fact a lot easier than studying these thermal bath systems which are highly chaotic. Okay. Suppose I very smartly engineer my system in such a way that suppose this is the state of the bath at t equal to 0. At some later time t equal to t, I engineer my system in such a way that at this point there is a formation of some whirlpool.
Whirlpool.
Yeah, a small, just a whirlpool inside the bath. Okay. So now suppose I go back again to t equal to 0. I do very small changes. Suppose like two water molecules at this position, I'm just swapping them, like a very slight perturbation that I'm doing to the system. Since this water bath is a highly chaotic system, if I again let it evolve the way I did it earlier, there's not going to be any formation of whirlpool here, because it is a chaotic system. Sensitive dependence on initial conditions, slight perturbation and drastic difference in the final outcome.
Yeah.
So you could take this whirlpool as this operator V.
Your analogy is a classical analogy because it's like.
Like chaos is chaos, right?
Chaos is chaos, but coming from classical to quantum.
I'm just giving an analogy, like how you can think about. I'm not relating any of it directly.
Yeah, okay.
Just an analogy.
Then it's fine.
Yeah, just an analogy.
Okay.
So you could think about this operator V as this whirlpool, okay, which should have and like this action of this operator W initially, like when I'm switching these molecules, you can analogously think, okay, I'm acting some operator W. This W will not give me the initial state, this initial state, just as this slight perturbation will not give me a whirlpool in the future. Okay, right. So this, when I forward evolve the system, if this system is chaotic, I'm not going to recover this.
Okay.
It could be anything, something really crazy, maybe some very big bump, I don't know, whatever. Let's say, for example, again the same thermal state back.
Okay.
It could be anything, but vastly different from this, if it is a chaotic system. Right? So this is how we can interpret this state psi 1.
Okay.
Okay, I hope it's clear. Now coming to the state psi 2. Now the interesting part. Now this was the more interesting part. This state psi 2 is not lot is happening, like not something very interesting is happening. Suppose I have my state beta.
You first, okay, you go on. Okay.
Yeah, of course. I'll complete my steps here. So when I forward evolve, there will be a minus iota. So the final thing that I get, this state will be described by e to the power minus iht omega. This should have been 0. I'm keeping it consistent. Like whenever I use this W operator, I'm going to act it at the origin and X. Okay. So when I forward evolve this system, I get 0 e to the power iht v, let's say x0 beta. This is my entire state. Now you could say, now you can switch your pictures and say, okay, this is how you exactly evolve your operators in the Heisenberg picture, so let me just call it W of minus t.
Because the expression is like that.
Yeah, no, like in a Heisenberg evolution, when you evolve the operators, this is precisely how you evolve the operators.
Yeah, that's it.
Right? You do not evolve the state.
Yeah.
So that's why I wrote my state as this.
Okay.
Right? Like I'm just very efficiently just switching my pictures to make physical sense of what this state is telling me.
Okay.
Right?
Yeah.
Everyone agrees with that. So this state is exactly what I've written here. Okay? Right. So now this state what this physically means is I again have my initial state beta. Now this state means go back in time. So e to the power ht beta. No perturbation, nothing. So the state will remain same. Now act with your operator W. Then you act with your operator W. You get W 0 e to the power iht beta. Forward evolve this system. So this again I'll pick up another I minus iht W 0 e to the power iht beta. Once I have this system, okay, now of course there will be perturbation. There will be a perturbation when I acted with W here. I forward evolve this system and I had taken my backward time such that when it goes forward, it has enough time to thermalize again. Now I act with my operator V0 and I get my bump.
Yeah.
This is what this is telling me.
Okay.
Right? So again, like this state by the time it is here, when I forward evolve, this is my W of minus t beta. Now I add my V0 and I get my bump.
Yeah.
Okay? So this, how exactly is this different from this? This says that suppose your system was initially engineered to have a whirlpool. I'm now talking in a very analogous language. Suppose the system was engineered to have a whirlpool. What you did is you went back in time, you added a very slight perturbation. If your system is chaotic, the state that you recovered after adding that small perturbation, you did not get what you had expected. You will not get the whirlpool. This is what this state means. This state means if you simply act your perturbation, whatever the system is, now you engineer it in such a way that this v equal to 0 appears at time equal to 0.
Okay.
Okay, so this is two different systems, and now since like there is nothing similar between these two systems, because I took the inherent assumption of chaos, this inner product vanishes.
Oh.
And this inner product is precisely the OTOC.
Ah, okay. The inner product of Psi 1 and Psi 2.
Inner product vanishes means they are orthogonal.
Orthogonal, like in a sense you could say, like there is no overlap. Like this state is completely different from this state.
Yeah.
Right?
Okay.
So this is how you can physically make sense of this OTOC vanishing, because I took this chaos. If had it been a non-chaotic system, I would have had some bump, maybe not exactly at time equal to 0, maybe some slight delay or something, But there, in that case, there would have been some non-zero overlap between these two states.
We would
The
have
non-chaoticness would not have made this vanish.
Yeah.
So OTOC vanishing is a diagnosis for chaos.
Okay. So anyone has any question till now?
Mm,
You have question?
OTOC vanishing. Yeah.
Okay. Yeah. So
OTOC vanishing means chaos.
Yeah, yeah.
OTOC vanishing, like OTOC.
Yeah, the commutator exponentially growing.
Uh,
Like if I want to remind you the
Okay,
relation.
okay. Here we are talking about large enough time.
Yeah, time which is greater than the scrambling
okay,
time,
okay.
such that it has some effect on me, right? I mentioned it.
It goes exponentially up.
The commutator goes exponentially up. OTOC vanishes.
OTOC, out of time order commutator.
Yeah, so like maybe this would be helpful. It takes this type of form.
Okay.
So like if this exponentially decays, since this is a minus sign, this will exponentially grow.
Yeah, that's why I get always confused because
Yeah,
yes,
yeah.
C is in both the terms, correlator and commutator.
Yeah, yeah,
So, okay, yeah.
So this is the picture. So if you want to talk about C of t, this would be the picture. And if you want to talk about OTOC, this is the picture.
Okay, so one is okay. C of t is your out of time order.
No, C of t is the commutator, which
Wait,
is
that-
given by this.
Yeah, it's out of time order commutator, right?
Here
Uh,
OTOC, here OTOC is inner product of
Yeah, yeah. The OTOC is this inner product. Like if you want to go back and see the actual expression, this is exactly what OTOC is. Sandwich between these two states.
CT is the correlator, right, or commutator?
CT is the commutator.
Okay.
It has a time ordered part
Okay.
and at the time out of time ordered part. Like out of time ordered part is the diagnostic for chaos. This is some non-interesting part. Which
That
we don't
OTOC
have.
you have written is correlator,
It is out of time ordered correlator, yes.
and then when you minus it, 2 minus OTOC is the commutator.
Commutator, yeah. Commutator is also a correlator, but it's just like it
has-
decomposes into two parts.
Two parts, okay.
One that is not interesting physically, and second which is all giving all the information about what is happening physically.
Okay, I think that's understood now. Finally, let's take a 2-minute break. Then we will resume the discussion.
Yeah. So this is the end of first section.
Okay.